Okay, so in this Excel tutorial, what I like to do is actually something very interesting. Many of you actually asked me if I could put something like this together. So this is based on popular demand. What I like to do here is actually do a couple of things. One is to show you the power of regression analysis, how powerful this tool is as a predictive model, and also how to do polynomial regression and be able to simulate data that you can model using mathematical modeling in Excel. So those are my two goals. Now the objectives I have listed here. One is to create a deterministic mathematical model. And I've decided on a third-degree polynomial just to make it interesting and not too complicated. You can go as high as whatever degree that suits your work. But I decided on a third-degree cubical polynomial model. Objective number 2 is to simulate the data based on a deterministic model, and that's probably what a lot of you are interested in. How do I simulate this data? And then in number 3, I would like to be able to fit a polynomial regression model in Excel through this data. And in objective number 4 is we're actually going to compare the estimated parameters from the Excel output versus the actual value of the parameters from the deterministic model. Now keep in mind, please, in practice, or as they say in real life, we don't know what the actual deterministic model is, and the model most likely will not be deterministic because anytime you sample data, you're bound to have error in sampling, and anything that's data driven is not going to be deterministic most likely. Okay, so on that note, I'm going to actually go ahead and show you the models that I have. These are typical third-degree polynomial models. And the betas are the ones that belonging to the parameters of the population. So I have beta sub 3, beta sub 2, sub 1, and beta sub 0, which is a constant. Now this is a third-degree polynomial model that we're going to do again. Now the sample regression model, of course, all those betas turns into b's for us. And the epsilon here, by the way, that's because we have a probabilistic model. Those are the error terms. Okay, so that's what those are, in case you wonder what the epsilons are. So these are the errors associated with each observation. And that error epsilon turns into E for the sample. So first of all, let me tell you about my mindset on how do I create a third-degree polynomial. So going back to my algebra days, this is what I was thinking. Okay, so I'm thinking about a third-degree polynomial function looking something like this. Okay, this is a very crude graph of it. I have a better portrait in just a moment for you. But that's what I was thinking, generate data from that. So this is how it all begins. Now, and then I went a step further and I said, well, why don't I make it behave like this? In other words, I want this third-degree polynomial model to have intercept at 0, 3, and 5. Okay. Now this is very basic intermediate algebra pre-calculus level work that I'm doing here. And then I actually decided, well, let's see, to make this amenable to a regression that's going to work nicely for us, why don't I shift this up a bit, make it more look like this. And of course, this part of it I don't need because usually with data, the scores are positive. So I would like to maintain my domain to be a positive input. Okay. So there you go, that's my thought process. So as for this function, the one that I have here, using pre-calculus techniques, I know that the x-intercept are 0, 3, and 5. So that would be my basic model. You see how I'm generating a mathematical model based on just the graph. And then this one, called it g of x. G of x is going to be f of x. And then I'm going to actually do this to it. I'm just going to add a scale, a constant multiple in front of it, and then I'm just going to let's go plus I don't know, k, and then I'm going to create a shift, and that's how it's going to go up. It's based on k. Okay, that's what's going to shift the graph. So this is what I'm thinking. Now, based on that, I actually created my mathematical deterministic model. Okay, so this is the very birthplace of my model. For that coefficient, I decided to go on 1/4, and then I have x minus 5, x minus 3, and then I decided to shift it up by 6 units, and I'm hoping to get again something like this. Okay, and you will see, because I will have a graph of what the function I'm proposing in just a moment. So this is going to be our, what I call my deterministic model. Okay, so this is something that, again, in real life we don't know when we just look at the data and the patterns that are in the data. Now, this model actually is going to turn into, once you distribute, do FOIL, distributive property, and you simplify this model, you're going to get 0.25x cubed negative 2x squared plus 3.75x plus 6. Okay, so this is the actual model that we're trying to arrive at using regression. So this is the model that we would like to, if you will, we would like to estimate using regression. Okay, so that's the basis of my work. Now, from here on out, I'm going to go to Excel, okay, and actually generate this. But before I actually go to Excel, let me show you what this looks like in using Desmos, another app, web-based app, to show you what the graph of this will look like. Okay, so now I am in Desmos, and I went ahead and graphed this thing. I plotted it. The function is right in here, 0.25 x minus 3 times x minus 5 times x plus 6. And notice that it's doing, the function is doing exactly what I envisioned it to do. Now, if I reduce the scale, there you go, you can kind of see what I had in mind. This is exactly what I had in mind. And again, for the work that I'm doing, I would like to just keep this portion, if you will. Let me make it fit. There you go. That's the portion of the graph that I'm interested in. Okay, so I'm just gonna copy this portion of the graph into my notebook, and then we move on to Excel next. Okay, and there it is. So here's our deterministic model, f of x. Now let's go to Excel and actually do what we're here to do. Okay, so now we are in Excel. So you can kind of see this is basic Excel environment. So I have a new sheet, and I named my sheet Polynomial Regression. Let me move this down, and you can see below here I have named it Polynomial Regression. So this is where I'm going to do the work. So first of all, let me paste these things. So these are the things that I'm actually going to need here. So, and throughout this video, I'll be using different features of Excel. So you can see hopefully the functions that I'm using, and you can see the procedures and the process of how I get things done. Now, let me also make a disclaimer. This is not the most efficient way that I do things. It's a way of doing it. As you know, there are so many ways you can do a task in Excel. So I don't claim it to be the most efficient way, but this is the way that I've done it, and this is the way that I will do it. So here I have my initial values of x. So I'm going to start with 0, and then I'm going to go 0.2, 0.4. In other words, I'm just going to go in increments of 0.2. Now, how far you want to go? I'm going to go until about 8. Okay, now why 8? Yes, I think that's a good number. It will illustrate what I want to do. It will show the portion of the graph that I outlined earlier. Okay, so these are the x values. Now, the actual values here are going to be based on our deterministic model, right? So I will need to create a column of x squared, so that's just going to be plus this, and then you square it. Okay, and what I like to do is I point often when I copy or write formulas, I copy from cells. Now, so that's what I did. That just squares the x. And then this one, I want to cube it. So I'm just going to go plus, point to the cell I want to cube. And that's how I cube a cell. Okay, the values in a cell. Now, I would like to copy everything down. So go to the lower right corner. You see this little plus sign. Double click, and it will copy everything down here. And just to check these nice integers, it looks like it's doing what I wanted to. Okay, and then I'm gonna shrink to fit, and I do a lot of cosmetics throughout my work, so please bear with me. Okay, and so there I have that one. Now, the actual values. Remember, the actual value is based on our deterministic model. So for me, it was plus 0.25, and then it was x cubed times x cubed, negative 2 times x squared, plus 3.75 times x plus 6. Okay, now some of you may wonder, well, why do you have x squared and x cubed? Why don't you just do this all in one step inside of that cell? And I could do that, but the reason I'm doing it the way I have, creating these additional columns, is because when we do multiple regression, we're going to need to have these to introduce into our multiple regression model. So that's why I'm creating these two additional columns. So please don't do what I just said to do. Don't put all of the actual value based on a single formula in a cell. Okay, now I want to copy this down, and let's see, just to make sure that in the copy process everything looks good here. And yeah, it looks fine. Okay, we'll find out, I guess, right, when we graph this. So these are the actual values. Now, next, we would like to look at the simulated values. So to do the simulated values, the way we do it in statistics is that we have the actual values. Okay, I have the actual values, and then what I want to do is I'm going to actually add some random disturbance, some noise around the actual values. Okay, so what I want to do is actually add to the actual values some random error, if you will. My errors are going to come from a normal distribution. You can decide what kind of error you want to have in your model. So usually we add random errors that are from a normal distribution. So that's what I'm going to do. Okay, so let's go ahead and do this. Here's where I'm going to generate simulated data for this model that we have. Now, to create the random errors for each observation, so I'm just going to go the actual here plus, and then I'm going to go the function you need. Excel function is norm inv, that as in inverse of a normal distribution. And you can read the description as you type in norm inv. It says this function available to blah, blah, blah. Okay, let's see, return the inverse of a normal cumulative distribution for a specified mean deviation. Now, let me hit parentheses. Okay, now the arguments that you need for norm inv is the probability here. So this probability is going to be anything between 0 and 1, and this, think of this as a percentile. Okay, so for example, if you put 0.8, that means you want to know what is the x or z score, let's say, because that's what we usually use, the variable that goes with the standard normal. We use z scores. So let's say I want a z score that's associated with 75th percentile. So I'm just going to put 0.75 in here, and then mean 0 deviation 1. Now, because we're simulating this data at every observation, what I want to do is I want to actually use a random, you go rand function. I'm just going to use a random generation mechanism to randomly generate the probabilities between 0 and 1. Okay, and so that's what makes it random, truly random for us. And then you hit enter, and there you go. So we got our first random observation for when x is 0. There you go. And then I'm going to copy this down all the way down to the bottom. Now, one thing about this process, by the way, every time you input into any cell, whether you put a new value or edit a new value, for example, look what happens here to all of these scores. I'm just going to punch in a number like 1, enter. And all of them change. You see all the numbers in this column change. I'm just going to delete this, and they change again. So what we need to do is we need to actually make these stable to where they do not change every time. Otherwise, our regression model isn't going to be able to keep up with this change. Because once you have the regression output, it's not dynamic, it's not sensitive to the inputs. So it's not like you change the input and the regression output is going to adjust to it. So what I need to do is I need to actually make these stay to where they don't change once I change the inputs in other cells. So this process is called hard coding your values, and to do that is the following. So what I'm going to do is I'm just going to highlight this column. Make sure you include all the values like I have. Okay. And then you can right click, copy, or Control C. Do copy. Now, make sure you go to that first cell. Don't go anywhere else. Otherwise, it's going to copy it in that other location. I'm going to copy it over onto itself. So click in this first cell, and then right click, and we're going to go to paste special. When you go paste special, there you go, and select values. So what this will do, again, it will hard copy those. They're no longer going to change. Okay, and there you go. You can escape out of this, and check this out now. When you go in that cell, look up here. You see that? You don't see my formula I had. Remember, I had norm, inv, and all that. So you don't see that anymore. And there you go. So this is how you simulate data from a normal distribution for our purpose. Now, what I need to do next is I'm actually going to run my regression analysis. Okay, now I don't have predicted values because we're going to run the regression. And then once we do, I'll be able to fill this column. So to do that, I'm going to go here, and I'm just going to type, I'm just going to go to up here, data, go data analysis, and there's regression, hit OK, and don't worry about these. When you first do it, you don't have these cells filled in. So this is what you're going to see, right? So my input Y range is going to be these would be like observed values of dependent variable, my simulated values. The simulated values are my dependent variable. Now, input X range, and to input X range, this is why now I needed 3 columns. So my X ranges now are going to be these. Okay, and that's it. Enter. Now, since notice my range includes labels, my first row are labels, that's good, because if you don't do that, then you're not going to get a descriptive output for independent variables or dependent variable. So make sure you check the label. If you uncheck it, we're going to get an error. So there you go. Make sure it's checked if you include the labels, which you want to do. Now, output range, I actually just point to this cell here. Now, some people actually determine, like, there you go, give it to me in this region or whatever. I just usually go to one cell and let Excel figure out the space needed to fit the output. and hit OK. Don't worry about other things. Now, I'm not gonna do a regression diagnostic for this problem simply because we are modeling from a deterministic model. So we're just gonna verify how good of a model we have by comparing the estimated coefficients from regression to those of the deterministic model. Hit OK, and there you go. So here's where the output is that we need. Let me change the color here to highlight it, and there you have it. And look at the r squared. R squared, that means the percentage of variation in y values, the simulated values, that are explained by presence of x squared, and x cubed. And this is 98.65%. 1, meaning 100%, is the max this number can get. So this is pretty darn well. It's an awesome model. It's doing what it's supposed to do. So it's an excellent model for prediction. And for those of you who are familiar with ANOVA, here the significance F, look at that, it's almost 0, right? 1.2 times 10 to negative 34, practically 0. And what this one does, what this F-test, if you will, does, it tests the global hypothesis that we have the right regression model for this problem that we're doing, and yes, we have the right model. Now, aside from that, let's move on to here to the coefficients. So this is actually what we want. This is our regression model. So our model is intercept, that's B0. It's 5.999. Remember that number was 6 from our deterministic model. The coefficient on x cubed, our deterministic model, was 0.25. This is 0.24. Very good, very close. In fact, when you look at the confidence interval here, it goes from 0.21 to 0.27. So the confidence interval clearly captures that 0.25. Okay, and look at the coefficient on x squared. The deterministic model was -2. The simulated model shows -1.92. And again, once you look at the confidence interval, check this out. It's clearly that -2 is inside of that range. Okay, and finally the coefficient on x was 3.75, and now it's 3.52, and it is within the margin of error. So this is really a good model. So let's do our predictions now. So for our predictions, I'm going to go plus. Remember, we multiply this number times x cubed. Make sure you go to the correct column here, times x cubed, plus this is the coefficient on x squared times x squared. This is the coefficient on x times x, and that should do it. Okay, something didn't go right. Hold on. Yeah. No, it looks good. Let me just make sure. I feel like one of the coefficients wasn't picked up. Yeah, let me do it again. So I'm gonna go plus constant term plus the coefficient on x cubed times x cubed plus the coefficient on x squared times x squared plus the coefficient on x times x. Now it looks good. Enter, and there we have it. So the simulated value was 6.3. The predicted value from regression is 5.99. And next I'm going to copy this all the way down. But before I copy all the way down, let me just copy just a couple of cells to show you something. These are actually inaccurate numbers, and you can see because look at actually the simulated numbers 5.47 at 0.2 and x is 0.2, and predicted is 0.36, which is way off. Now if you go in that cell and double click, you kind of see what the formula is doing now. So the formula is multiplying, well, it's doing N20. Cell N20 is this number. See, everything is shifted down 1 because I copied the cell down 1 space. So everything is shifted down. In other words, we're getting inaccurate information because cell addressing is relative in Excel. So as you copy things, then the cell address will adjust itself to the new range. Now, what we want to do is we want to freeze these cells, the ones that involve the coefficients. We want to freeze them, and we're going to allow the other cells, other numbers, to vary depending on the value of x. So here's how we're going to do that. We're going to go to, okay, n19, that was our constant. We want that to be fixed for every cell. It's a constant, plus n20 is the coefficient on x cubed. So we want to freeze that cell. You do that by putting the $ before and after n. And here, $ before n freezes the column. This one freezes the row that it's in, that entry. And finally, freeze the column and freeze the row 22 of the coefficient on x, and hit enter. Good. Now let's copy this, and I'll show you as we copy. If you look, notice the numbers are more sensible now. Okay, you can see that. But let me go here, for instance. Look at this one. Okay, what this is doing is it's multiplying. Well, it's doing n19, the coefficient on the intercept, that's the constant, plus n20 is the coefficient on x cubed, times d9 times 1. So it's doing what it's supposed to be doing. Okay, and perfect. So there we have it. Now, what I want to do here, I've created a column of difference between the actual and predicted values. The actual is off of the deterministic. Okay, so be mindful here, folks, for those who know about the regression. This is not a residual, what I'm doing. The residual looks at predicted minus the observed value, right? The difference between these two is what's called the residual in regression. I'm not doing that. I'm looking at the difference between the actual deterministic value minus the predicted value. So it's really not a residual for regression. And look at that, that's pretty darn good. Copy it all the way down, and some of these, the numbers in this column, should not be 0. It won't be 0, but look at how far off we are from the actual deterministic model. The total miss is about 2. Remember, this isn't going to be 0, unlike residuals that sum to 0. So there you go. That just tells me this is a good model. Now, let me actually create the graphs, and we check this thing out on the graph and see how things go. So to do a scatter plot, I'm going to highlight X column, simulated and predicted. Oh, yeah, that's fine. I was going to put actual, but you've seen what the actual looks like, right? Remember, I went to Desmos and did that. So we know what the theoretical model, the third-degree polynomial, looks like. Okay, so to do a scatter plot, so I highlight the range, then I'm going to go insert, and then right in here, I'm going to go scatter plot, and voila, there you go. Isn't that gorgeous? There you have it. See how nice that looks? So you're looking at the blue is actually, I call it simulated value, but it's actually your observed values. And the red is the predicted values. And you can see how well this regression model has done in predicting. Look at that. So again, the red is the regression model. It looks almost like our deterministic model. And in fact, what these are like the coefficients on a Taylor polynomial that we're looking at here for third degree Taylor polynomial. And that's what we wanted to do. So what we've done here, in fact, is we illustrated how to run a regression analysis, sort of. We just want to see how we can simulate data. That was what we did in this column. Okay, and then we looked at how well the regression model fits the real function. So that's all we wanted to do. So I hope that you find this useful, and now you'll be able to generate your own data for any function of any type that you like to. And with that, we are done with this video.